2, lesson 321 introduces trigonometry, and it really is the study of right triangles and similar triangles kind of mashed together, and they discovered some other things about right triangles. So essentially, if we have the Pythagorean theorem, we know that a squared plus b squared equals c squared, and we know that if we have similar triangles that they have to be proportional side lengths. So they sort of figured out the two, and they said, all right, well, what if we have these two triangles that look like this? Then we know that if this distance, if we call it x, and this distance we'll call it x prime, and this distance if we call it y, and this distance we'll call it y prime, and this if we call it z, and this distance we'll call it z prime, we recognize that there has to be like a ratio of similarity to make these things work, because we have similar triangles, right? We have angle similarity, so the sides have to be proportional. So they kind of realized that hey, look, anytime we have a right triangle, all right triangles are proportional if they have the same angles. So what I mean by that is, if I extended this out again, and kind of kept going with an even bigger right triangle, this too would have the same proportions as these two smaller triangles, right? Because they still have angle similarity. And if I keep going, all of these triangles have the same angle similarity, which makes all the sides of these different sizes triangles proportional. So what they did is they realized if they figured out what those ratios were and sort of divided one side by the other, they would get a common ratio. And if they always got the same ratio, they would be able to determine the angles. So that really is kind of the idea of trig. When we look at the Pythagorean theorem, and I'm sorry, I know I talked in circles here, but when we look at the Pythagorean theorem, we're talking about side lengths. When we look at trig, we're looking at how the side lengths make a ratio, and that ratio is always the same, and that will drive us to the exact angle that we're looking at. So again, what we're going to do with trig is we're going to take these side lengths, and we're going to divide them by each other, and take these side lengths and divide them by each other, and that'll give us a ratio. And with that ratio, we're going to look at a chart, and it'll tell us what angle we're looking at. And I want to point out here that, what if I change the colors here? What if I divide this side by this side? Well, then I'm going to get a different ratio, but I should still be able to do the same thing, right? All these sides are proportional to each other, but if I do the x sides, I'll get one ratio. If I do the y sides, I'll get another. And if I do the z sides, I'll get another. So as long as I understand that, I should be fine on that. So I think I did a terrible job of introducing trig. I apologize for that. I'm going to pause this video, and then we will jump into it. And again, I really want you to just keep in mind how those ratios are always the same, and that allows us to calculate angles. That's really the whole thing of trig. So I think I overcomplicated it. So the Leaning Tower of Pisa. For centuries, people have marveled at the Leaning Tower of Pisa due to its slant and beauty. Ever since construction of the tower started in the 1100s, the tower has slowly tilted south and had increasingly been at risk of falling over. It is feared that if the angle of slant ever falls below 83 degrees, the tower will collapse. Engineers closely monitor the angle at which the tower leans. With careful measuring, they know that the point labeled A in the diagram at right is now 50 meters above the ground. So they must like drop a string and know the length of that string, so they know it's 50 meters straight to the ground. Also, they determine that when the angle is dropped from point A, when a weight is dropped from point A, it lands 5 meters from the base of the tower. So they have this triangle figured out of 5 by 50. You'll notice it's a right triangle, as shown in the diagram. So with the measurements provided above, can you determine, what can you determine? Well, I think we would definitely be able to determine this length right here, right? 5 squared plus 50 squared would equal this length squared, the hypotenuse length squared. Again, the hypotenuse is the side opposite the 90-degree angle. Can you determine the angle at which the tower leans? Why or why not? Well, you actually can determine the angle at which the tower leans, but you have to use trig, and that's what we're going to learn, is that this triangle has to have a certain ratio, and when we calculate what that ratio is, we can, someone did all the ratios for us. They made a chart. Actually, let me pause and show you that. Of all the angles and the different ratios that they have. And anytime that we measure cosine, and we'll talk about that more later, But anytime we measure cosine and we get a 0.9962 ratio, we know it must be a 5-degree angle. And anytime we calculate tangent, again, we'll talk about that later, and we get 0.2679, we know we're looking at a 15-degree angle. So they calculated this for all 90 degrees. And this is what we're going to use to be able to, again, figure out that side length ratio. So once we have that ratio, then we can figure out the angle. Actually, I should also mention, if we have an angle, well, then we can use the ratio to figure out the side length too. So it sort of goes both ways. If you give me two side lengths, I can tell you an angle. If you give me an angle on a side length, I can tell you the other side length because they make those ratios. It's kind of neat. Hopefully it'll make sense as we get into it. All right, it says at the end of section 3.2, you will know how to determine the angle for this situation and many others. However, at this point, how else can you describe the lean of the leaning tower? Well, I mean, like I said, I don't know. We can definitely figure out this length here. How can we describe the lean? I guess we could get the equation of a line, right? We could put this on a coordinate grid and sort of get a point here and a point here and write the equation of the line that goes through them. It doesn't seem like we're actually asked to do any of that, so there's a lot with trig, so let's just go ahead and move along since we're not being asked to actually do that. So it says patterns in slope triangles. In order to determine an angle such as the angle at which the Leaning Tower of Pisa leans, you need to investigate the relationship between the angles and the sides of a right triangle. You will start by studying slope triangles. Obtain the lesson 3.2.1 resource page and locate the graph shown below. Well, we already have it, so no big deal. It says, notice that the slope triangle has been drawn for you. Note, for the next several lessons, angle measures will be rounded to the nearest degree. So that's important. I know I showed you guys this trig table. This is all rounded, so it's not exact, and that's fine. That's why it goes to 4 decimals, 4 digits after the decimal, because we are rounding, so we want to be as precise as we can. So it says now draw 3 new slope triangles on this line. Each should have a different size. Label each triangle with as much information as you can, such as the horizontal and vertical lengths and the angle measures. Well, here's the thing. If I can go over 5 and up 1, what if I go over 10 altogether? So 5 more, 1, 2, 3, 4, 5, and up 2. Now I know that this one is a length of 10, and this has a height of 2. Or if I change colors, I can go over 5 more. Uh-oh, 1, 2, 3, 4, 5. I lost the straight line tool. Now I'm going over 15, and I'm going up 3. What if I go over 5 more? 1, 2, 3, 4, 5, and then I should be going up 4. And that's 20 over 4. And again, look at these ratios are the same. The black one has a ratio of 1 to 5. I don't know if there's like sort of pinkish or whatever, has a ratio of 2 to 10. The red one has a ratio of 3 to 15. And the green one has a ratio of 4 to 20. Either way, they all have the same ratio, right? If we simplify that, we get the 1 to 5 ratio. It says explain why all the slope triangles must be similar. Well, because they all have this 11 degree here and the 90 degree here. So we have angle similarity. Since the triangles are similar, what does that tell you about the slope ratios? Well, the slope ratios must all be the same because they're similar, they have the same size. So it says confirm your conclusion by writing the slope ratio for each triangle. Well, I did. I went rise over run. Up 1 over 5, up 2 over 10, up 3 over 15, up 4 over 20, and we did confirm that they're all the same. So let me go ahead and set up the next. I actually did tie in as much as I wanted to. Is obviously we have all these different slope triangles, right? And the thing is, this angle is always 11. I think I said it, but I didn't really drive home that point. So this angle is always 11. This angle is always 90. So this top angle must always be 79, right? Because of the triangle angle sum theorem, the fact that all triangles add up to 180 degrees. So that's going to become important more later, but I really want to drive home the fact that that angle is always 11, that angle is always 90, and that angle is always 79 when we have that 1 over 5 ratio, right? Thinks she sees a pattern in these slope triangles, so she decides to make some changes to investigate whether or not this pattern remains true. And we've already seen that the ratio was 1 to 5 and 2 to 10 and 3 to 15, and 4 to 20. Uh-oh, that doesn't look good. Ugh. Man, this video is a debacle. I apologize. All right, so what if the y was 6? And remember, it's change in y over change in x, so the y would be on top. So what if it was 6? Well, we're just multiplying by 5, right? So it would be 30 on bottom. And what if the x was 40? Well, then we would just divide by 5 and we would get 8 on top. Tara wonders, what if I draw a slope triangle on a different line? Can I still use the same ratio to calculate the missing x or y value? Discuss this question with your team. I mean, I guess as long as she was still going with the ratio of 1 to 5, it wouldn't matter, right? If she kind of changed it and went over 1 and up 5 and over 2 and up 10, or over 1 and 5, up 2, up 10, up 3, 15, it should be the same. It shouldn't really matter as long as she keeps that ratio. All right, so changing lines. In part C of problem 369, Tara asks, what if I draw my triangle on a different line? With your team, investigate what happens to the slope ratio and slope angle when the line is different. So use the grids provided in your 321 resource page to graph the lines described below. So use the graphs and your answers to answer the questions to respond to Tara's question. So on the graph, what we're going to do is we're going to graph y equals 2 over 5x, and we're going to get the slope ratio for this. And then what does this slope angle appear to be? And what we'll do is we'll measure that and see what we come up with. So let's go to y equals 2/5 x. This, you would see that the slope triangles would be essentially the same, right? We still have those similar triangles. And if you grabbed a protractor, you would see that you come up with it about 22 degrees. So that's important to know. 370 B and C, to do a protractor would just not be really practical. What we're going to see is they always have the same ratio. This is probably the worst video I've ever made, and that's saying something because I made a lot of videos, but this is not going well, I don't think. So hopefully when we add some more to trig, it'll make a little bit more sense, and maybe I'll be able to reiterate my point a little better in the future. So it says a student in Ms. Coiner's class are writing conjectures based on their work today. As a team, decide if you agree or disagree with each of the following conjectures. Explain your reasoning. So all slope triangles have a ratio of 1 to 5. No, we drew one that was 2/5 too. So, but if a slope ratio is 1/5, then the slope angle is approximately 11 degrees. Yeah, all the ones that we did that had that 1 to 5 or 2 to 10 or 3 to 15, they all have that 11 degree angle. If a line has an 11 degree slope angle, then the slope ratio is approximately 1/5. Yep, that's kind of cool. So think about that. If you have a grid, right, and you want to make approximately an 11 degree angle, you just simply need to go up 1 and over 5 and connect those dots, and you'll have roughly an 11 degree angle. I guess I should say you'll have about an 11 degree angle. It's that simple, right? So that's part of the beauty of trig, and that's really, I think, this point right here drives home the whole video. If you can get this point, I think the video is worth it. If you go over, I'll say that again, if you start at a point and go up 1 and over 5 and connect those lines, you have basically made yourself an angle that is approximately 11 degrees. And that's one of the things that trig tells us, that if you have a ratio of 1 to 5, it's about 11 degrees. If you have a ratio that's 2 to 5, it's about 22 degrees. And different angles have different ratios. Again, different angles have different ratios, but they're always the same ratio. So it's just a matter of figuring out what ratio goes with what angle, and then we can do trig. All right, so different lines will have different slope angles and different slope ratios. I think that's a yes. I'm not really sure. Different lines, well, I mean, some might be the same and some might be different, but on the whole, I guess there are different slope angles and different slope ratios, but the slope angles and slope ratios always go together. So I'm not sure if I'm misreading this question or not, but ultimately that's my point. Thank goodness this video is done. I'm tired of it.